Lightsabers. Few items in sci-fi are as instantly recognisable. The hilt rises, and then there's that characteristic snap-hiss ignition as a glowing blade of pure energy erupts. It's elegant, deadly, the weapon of a Jedi Knight. But could it ever be real? Could science give us a handheld blade of energy? Today we'll look into that science. We'll look at how lightsabers work in the Star Wars lore, and we'll compare that to real science. We'll look at plasma science, lasers, magnetic fields, energy storage, and material science. And we'll ask, what would it take to build one? And why the dream is harder and stranger than you might think. So, how do lightsabers work in Star Wars? In the Star Wars canon, a lightsaber is more than a weapon. It's a rite of passage, each Jedi constructing their own. Inside the roughly 30cm hilt, there is a power cell and a Kyber crystal that focuses the blade, an emitter and a containment field that fixes the length of the blade to somewhere around a meter, and a load of various control electronics and gubbins as well. The fictional bill of materials for a lightsaber looks something like this, therefore. A power source, a very small power source, a focusing crystal that somehow shapes energy into a blade, an emitter that projects the blade outwards, a containment field that stops the blade at a set length, and some way for the energy blade to clash with solid objects. On screen, it works perfectly. The real science, however, is a little more challenging. So, we want to make our own lightsaber. How might we do this? First, let's try lasers. Lasers have two real problems. Problem 1, lasers don't stop. Photons fly on until they hit something. Without some sort of end cap in mid-air, a laser blade is just a torch beam that goes on forever. Problem 2, lasers don't collide. Two laser beams would cross without exerting any force on each other. Yeah, there are exotic non-linear effects where light can interact with light, but these are at intensities far beyond anything handheld. These occur mostly in particle accelerators. So, while lasers can burn and cut like a lightsaber, a true meter-long solid energy blade is not a laser. Would plasma work? This idea is more promising. Plasma is ionized gas, electrons stripped from atoms, like lightning or the substance that makes up the sun. It glows, it conducts, and at tens of thousands of degrees it can easily sever steel in a blink. We already use plasma cutters. They blast a jet at around 20,000 degrees Celsius and chew through metal. But that jet is open and uncontrolled. It doesn't stop at a tidy 1 meter. To sculpt plasma into a sword blade would need what's called a magnetic bottle. Magnetic bottles are found in tokamak and stellarator fusion reactors. They are coils of superconducting wire which generate magnetic fields that guide charged particles along invisible rails. Inside these reactors, temperatures can exceed 150 million degrees Celsius, yet the plasma never touches the walls of the reactor. So, all we would need to do is shrink a fusion reactor, which at the moment is typically building-sized, into a 30cm hilt. That's the first challenge. How strong would the magnetic fields need to be? Let's run a simple sanity check. Charged particles spiral around magnetic field lines within what's called a Lamarr radius. This radius is equal to mv over qb. So, if you want a tight, let's say 5cm wide lightsaber blade, R must be a few centimeters. At 20,000 degrees Celsius, ions will be moving at several kilometers per second. So, to keep R, the radius, down 2 centimeters, you'd need magnetic fields on the order of several Tesla or more, and a careful field geometry so particles don't escape at the tip of the sword. 1 to 3 Tesla is similar to what an MRI scanner generates. Tokamak reactors are stronger. Handheld coils at those field strengths would be extreme. Now let's consider the tip-stop problem. A real lightsaber blade must end. Field lines must loop back without letting the plasma spill. That means nested, curved fields. a mini tokamak reactor essentially, with a return path so the plasma doesn't just diffuse. Designing that magnetic topology inside a palm-sized hilt is not easy. What sort of energy are we talking for our lightsaber? How much power would a lightsaber need? Let's bracket it two ways. First, radiative heat flux. At 20,000 degrees Celsius, plasma radiates like a blinding furnace. Even at far lower temperatures, the radiant power hitting the hilt, and therefore the Jedi Knight's hand, would be catastrophic without heavy shielding. Second, stored thermal energy. Rough model, let's say a lightsaber 1 meter in length, 5 centimeters wide. That would require 2 times 10 to the minus 3 meters cubed of gas. At plasma temperatures, the internal energy per unit volume is therefore huge. Back of the envelope, you'll be holding hundreds of megajoules of hot matter, assuming it's dense. If it's low-density plasma, the instantaneous power to keep it hot is still enormous because the blade would constantly lose heat by radiation, conduction, and convection. Let's look at it a different way. The sun's surface radiates approximately 63 megawatts per square meter. A lightsaber would have similar multi-megawatt power levels, something uncomfortably high for something small and battery-powered. Talking of batteries, we should probably do a bit of a battery check. Modern lithium-ion batteries store around 250 watt-hours per kilogram. 1 minute of lightsaber use at even 10 megawatts would require 167 kilowatt-hours of energy. This would therefore require hundreds of kilos of the best batteries available today just for 1 minute of use. We can't shrink those hundreds of kilograms of batteries down into the hilt. Not at the moment, anyway. So, what we're really saying here is that a real lightsaber would need a small fusion reactor to power it, not AA batteries in a tube. Focusing. What could our Kyber crystal be in real life? In the Star Wars lore, the Kyber crystal focuses and tunes the blade. What can real science use? Maybe photonic crystals? These are structures that steer specific wavelengths of light. Maybe metamaterials. These are artificial composites that bend electromagnetic fields in unusual ways. Or maybe high-Q superconducting resonators. These are cavities that concentrate microwave or RF fields with very low loss. A plausible real-world analogue is therefore not a magic rock, but a field-shaping core. This core could be stacked metamaterial layers and resonators that route RF microwave power into a stable magnetic cage. And you know what? We haven't really talked about colour. In Star Wars, the colour comes from the Kyber crystal. In a real lightsaber, the colour could come from plasma emission lines, maybe. A pink-purple lightsaber would come from a hydrogen bomber line, or maybe from additives in the plasma gas. For example, sodium additive would make a yellow lightsaber, copper a greeny-blue lightsaber. How do we make our lightsaber solid so we can use it to duel? The force between two lightsaber blades must exceed the user's arm force, easily hundreds of newtons, during a clash and parry between a Jedi Knight and a Sith Lord. 2 unconstrained plasmas would just interpenetrate. 2 laser beams would just pass through each other. For the 2 blades to resist each other, you'd need the fields to strongly repel where the blades overlap. One idea? You could maybe engineer each blade's magnetic bottle so the outer field is high pressure and mutually exclusive. When the fields touch, they push apart, like trying to force together the poles of 2 strong magnets. That could produce a virtual surface where the pressure feels solid. But this would demand precise phase, frequency and geometry matching between 2 independent weapons whilst they are in motion at arm's length. If the phasing were to slip even a little, the blades would pass through each other. Or worse, one could destabilize the other catastrophically. Cinematic, yes. Practical, no. So, even if we nail the fields and the energy beam, the hilt still sits centimetres from something radiating like the surface of the sun. What keeps the hilt from melting? Maybe we could use ultra-refractory materials. Tungsten, hafnium carbide, ceramics maybe? These would get us to maybe 3,500 degrees Celsius. But these are still far below plasma temperatures of 20,000 degrees Celsius. Maybe we could use active cooling, phase change heat sinks, micro-channel liquid cooling, and cryogenic loops with superconductors. Maybe we could use radiation management, polished reflective shields, nested baffles, and sacrificial ablative liners. Radiant heat falls with distance, but a metre-long 10,000 degrees Celsius object is basically a portable Jedi barbecue. Realistically, you'd need insulated gloves, visors, and a radiation suit. Jedi robes won't cut it, I'm afraid. What about that signature sound? That signature hum of the lightsaber could actually be easily achieved. The AC power driving the magnetic fields, plus the plasma acoustic noise, may well produce something close to that hum. It's actually the one requirement science could realistically fulfill now, today. It may surprise you to know that there have already been real-world attempts to make a real lightsaber. So-called plasma protosabers have been constructed. These are retractable, flamethrower-like plasma torches, powered by backpack gas tanks and heavy batteries. They can scorch and cut, but the blade is an open jet that doesn't stop at 1 metre and cannot be used to duel with. Industrial plasma torches routinely exceed 4,000 degrees Celsius and will slice steel plate, but they require compressors, a gas supply, cooling, and significant distance from the operator. And unfortunately, turning that into a one-handed sword is impractical. So, what does a plausible roadmap to a future lightsaber look like? If we insisted on building the closest possible thing, the roadmap might look a little bit like this. Step 1. Construct a field core for the lightsaber. We would need to develop a palm-sized magnetic bottle using high-temperature superconductors. The target would be a multi-Tesla field in a 5 centimetre radius, with shaped return paths forming a rounded tip to the sword. Step 2. Construct RF heating. Use microwave RF power to ionize a low-density gas to maintain a bright plasma column. The target would be a visible bright plasma without a catastrophic heat load on the hilt, i.e. the plasma would be optically bright but tenuous. Step 3. Construct a power module. We would need to swap out batteries for a compact fusion microreactor, which would give us kilowatts to megawatts of burst power. This would need to deal with intermittent ignition windows, which could limit the average load on the power module. Step 4. Construct thermal armour. We would need layered reflective shielding, aerogel spacers, micro-channel coolant, and ablative edges at the emitter for the hilt to survive straight plasma. Step 5. Construct interaction fields. We would need to engineer the outer field so that 2 blades would repel each other strongly, enough for them to block each other. Step 6. Everything else. Even with all the things we've just mentioned, and a working lightsaber in our hand, the device would be very heavy, very loud, and terrifyingly dangerous, and still far from the effortless elegance we see on the screen with Luke and Obi-Wan. For the field strength of our lightsaber, we would need handheld multi-Tesla magnets. These are possible, but quenching and cooling will be hard. For the power, a 1 to 10 megawatt burst is currently industrial scale. Portable power would need to be thousands of times smaller than is currently possible. For the heat, radiant flux from a white-hot metre-long lightsaber is the difference between cool sword and why is my house on fire? Many of the things, though, that we require are exactly the things which science is improving on each year. High-temperature superconductors, metamaterials, compact RF sources, and advanced ceramics, for example. Even if the real science says not today, lightsabers do something powerful. They focus our curiosity. They get kids and scientists to ask about plasma, about magnets, about energy. They drive interest in fusion research, in material science, in power electronics. They connect imagination to engineering. Science fiction doesn't need to be perfectly accurate to be perfectly useful. Star Trek communicators became smartphones. Tablets became tablets. Voice assistants, holographic displays, gesture controls were all seeded by science fiction. Maybe a true dueling lightsaber will always be a fantasy. Maybe not. But the path towards it will definitely spin off real technologies that will change how we power cities, build spacecraft, or perform surgery. So, can a Star Wars lightsaber exist? With today's science, no. Lasers don't stop, plasma won't sit still, and handheld reactors simply don't exist. And dueling demands field interactions we can't yet produce outside a lab. But each part of the puzzle is tied to real physics, real science. Plasma confinement, magnetic field design, energy storage, high-temperature materials. As those advance, what's impossible now may become possible. Maybe we never build the perfect Jedi weapon, but a plasma tool that looks the part for cutting and welding, that could arrive sooner than you think. Until then, ignite your curiosity, not your living room, and may the real science be with you.